Okay, welcome back, students. Hope you're doing great. So I guess this is the third lecture that we are going to have on uh, microprocessors. And in this, okay, before starting, uh, what we are going to cover in this lecture, uh, in the first lecture which we conducted last week, uh, online, I mean while live streaming, was about the basic programming model or programming environment that a microprocessor provides us to a system or application programmer. In the second session that I just uploaded today is about the memory, sorry, not memory, the microprocessor operational modes or modes of operation like real mode, protected mode, and system management mode. In this lecture, we are going a bit further and we'll discuss about the execution environments. Okay, like the execution environment is basically an environment which is uh, provided by the operating system to any process that were intended to run. Like for instance, you have open any application, like any, like for instance a text editor or a PowerPoint application or MS Word. So what happens behind the scene? Operating system uh, provide an execution environment so that that process can easily run and you can get the required output. So in this lecture we are going to talk about the execution environment that is provided by IA32 microprocessors like Intel architecture 32-bit. So the first thing, okay, let me tell you, the execution environment is basically provided in by the operating system in conjunction with the underlying hardware, you know. So the first thing that we will let's discuss about the uh, access to CPU, right? When you run an application, so the application, in the whole hardware, in your PC, or if you have a PC or a laptop, there are different hardware components like motherboard, RAM, processor, IO cards, hard drives, USB storage, mouse, keyboard, display, etc. So among all these hardware components, the CPU is the component that actually executes your instructions. So any process that's want to run on a machine, so it must have that process need access to CPU. This is the first thing. The second thing, the code of the process or code of the program. The program which you want to run must be loaded into the RAM. The program which you want to run must be loaded into the RAM or memory. So the application code must be loaded into the memory, and definitely the application code or the code generally use some data that may be read from the hard drive, okay, or maybe stored back to the hard drive. And everything is actually stored on our secondary storage devices like hard drive. So the program is loaded from the hard disk to the RAM, okay, and it for any persistent storage, any data that the process or program or application want to store for permanent availability or for long-term availability must be stored in the RAM, into the storage unit like hard disk or USB. So similarly, the process will require storage accesses, and it must require some storage blocks. And similarly, maybe some of the application or services running to provide some access like HTTP for browsing, or some file services like FTP. Okay, so these services like need to have access to the network. So in the nutshell, these 3 to 4 are the basic resources that must be provided by by the operating system for any task or any application want to run. Okay, so all these components that we have just discussed make up the execution environment for any microprocessor, irrespective if it is a IA32 or a 64-bit, or it's an ARM processor or some other hardware, embedded hardware, something like that. But some of them are definitely required, if not all. Similarly, when we talk about the Intel 64-bit architecture, so all those things that we just discussed in the previous slide will be required for, will be required for any process want to run on the machine. So but definitely 64-bit architecture is a bit different. Their execution plan and some other requirements get changed depending upon the process as well. So but if we talk about a 64-bit processor, so 64-bit processor generally provide us 2 to 3 main features. One is the environment for the execution of 32-bit applications like legacy or traditional IA32 applications. And the new feature, obviously the notable feature of a 64-bit microprocessor is to provide an environment and execution environment for a 64-bit application. But as we saw in the previous lecture, for the compatibility reasons, okay, for backward compatibility, it provides features and the execution environment for 32-bit and even 16-bit applications as well. So in the previous slide, we talk about the execution environment that a process needs to have when it must be running. So like access to CPU, access to memory for loading and storing data temporarily, for permanent storage it must be required for hard drives or USB or flash drives. And in case like we can say that if a process wants to access some network resource locally or via internet, so it must require network access as well. So all these things are also required for a 64-bit application as well. So from the microprocessor point of view, we can list down few basic elements that must be provided for an application, like address space, access to different execution registers, the floating point unit, MMX, XMM, YMM registers, some other sort of registers, IO registers, IO ports, etc. So we'll see these things in bit detail one by one. So let's talk about first of all address space. So address space is actually the set of memory addresses, and we can say that set of maximum possible memory addresses. So whenever any process or a task is running on IO 32-bit processor, can actually access the storage, here storage I mean RAM, with the help of linear address space model. We have a complete lecture on memory models, but here we will discuss few things briefly. So a linear address space says that uh, it will it will it will take the whole RAM. It will consider the the complete RAM, random access memory, which is attached to the motherboard, as a linear array of bytes. So since the maximum available uh, RAM or memory that a 32-bit processor can access is 4 gigabyte, 2 to the power 32. However, with the help of physical address space extension, physical address extension, a 32-bit machine like IA32 processor running a 32 running running an operating system can basically access up to 64 GB of RAM with the help of physical address space extension. And obviously, as we covered protected model and the real model in the previous lecture, so it must be in the protected mode, not it is not possible in the real mode. And here these are the two conditions. So in order to access beyond 4 GB of RAM, the processor must operate in protected mode, as I said, and the virtual memory management system or virtual memory management technique must be enabled. We'll see virtual memory management technique shortly. Alright, so general purpose registers, segment registers, and E flags, all the basic program execution registers were covered in the first lecture, if you recall it. So if you have any query regarding the general purpose registers, special purpose registers, flag registers, you can refer to that lecture, and if still there is some confusion, you can contact me. Okay, the new thing, there are a few new things that we are going to study from processor perspective, and the first thing that you'll see now is floating point unit. So in IA32 based processors, there is a floating point unit x87. So a floating point unit actually perform floating point instructions. It executes floating point instructions, and this is a complete unit. This is a complete component on the microprocessor, and it has a separate set of registers. These are separate registers. These are not microprocessors general purpose registers, nor they are special purpose registers. They are an x87 FPU contains 8 data registers, 1 control register, 1 status register. It has its own IP instruction pointer register. It has on operand pointer register, tag word register, and opcode register. So the thing that you need to grab over here is it provides an execution environment for operating on single position data type like float, double position like double in C, and here we have double extended position floating point. This might be new for you. A word in integer like 16-bit integer, then double word integer like 32-bit integer, quad word integer like what I say like 64-bit integer, and finally the last thing over here is binary coded BCD values. Okay, so all right, so MMX registers. I hope you have completed the second assignment which I gave you, like the assignment that talks about the evolution of 8086 microprocessor series, and if you have completed that assignment, then you might studied or might aware about MMX technology, multimedia extension. All right, so what is multimedia extension? All right, students, we were discussing about MMX technology. MMX technology was actually introduced by Intel, and the purpose of MMX technology is to operate on integer data types. Yeah, integer. So what's the difference? The difference is the SIMD technology, SIMD classification. uh, in 70s, uh, let me tell you. In 70s, Flynn proposed a taxonomy for multiprocessor based systems. Okay, and in that taxonomy, there was one type of multiprocessor based technique was SIMD. Okay, SIMD stands for single instruction multiple data. Okay, let me give you an example. In some scenarios you want to operate on, you want to perform a same set of operation on group of data. Like for example, if I like for example, let's take a image processing example. Okay, for example, in this image processing example, you want to basically scale down the, let's suppose, the intensity of all the colors. Okay, so what you have actually, you have a matrix of pixels. This is row, this is column. Okay, and you want to perform a same set of operation on all the pixels, right? Or the intensity of the or the colors of the pixels. So what you have here in sim, as I said, sim means here in some scenarios you want to perform same set of same operation, single type of operation on a group of data. Let's say that you want to calculate uh, an average of multiple linked list. What I mean, like you have, let's say that here you have 4 lists, L1, L2, L3 and L4, and all of these lists contain some integer values, or let's say floating point values. So, and you want to calculate the average. So here the operation is average, and that average operation which you want to perform on all of the list. So here this say the operation is single. Okay, this is single operation that you want to perform, but the data is different, multiple data. So this is known as SIMD classification, SIMD type of multiprocessor. Okay, so going back to the MMX technology, Intel actually introduced MMX technology, and they said their architecture now started to support SIMD operation on 64-bit packed byte word and double word integers. Now the second new thing that you will see in this slide is a packed byte. As we have just discussed that SIMD requires multiple data. Okay, like if for example, if in a code you want to perform an operation on a single variable, like for example you have a code integer a semicolon, and you want to actually divide that variable a by 2, for instance, right? So let's see, integer d is equal to a by 2. But this is a single instruction and single data. This is a instruction is the division operation, is the division operation, and the data is a. But since if we want to perform SIMD operations, so we need multiple data. So for multiple data we need multiple operands a, b, c, d, and we want to divide all these operands by 2 as per this instruction. So this data is actually packed data, and here if this integer takes, let's say, 4 byte, means double word, then we can say that this is a double word packed data, or a quad word packed integer, or double word packed integer. So the problem with the MMX technology was it could only perform on integer, so that was a limitation. Okay, so that was a limitation, that the MMX technology, MMX only works on integer data type. And definitely for MMX technology, the microprocessor need registers. Okay, so that's why I have mentioned that there will be some MMX registers in the microprocessor. So they came up with something new, and that was XMM technology, Extreming Multimedia Extension. Okay, so the new thing about streaming multimedia extension, or streaming instruction SIMD is streaming SIMD extension. Okay, can these instructions, or these operation can perform on floating point as well. Okay, so that was a new thing. So in order to perform SSE operations, okay, the microprocessor need XMM registers. Okay, I think let me go back to the previous slide. Okay, we have MMX. Okay, we have, in the next slide, we have SSE, streaming SIMD extension. I guess, if I'm not wrong, I'm recalling the right acronym, I guess. And before that we discussed about SIMD. Okay, so I think SIMD is clear to everybody. SIMD means single instruction, single type of operation that is going to perform on multiple data, multiple different data. Okay, so both are almost same thing. The difference is MMX. In MMX, SIMD is performed on integer pack type data, integer data, we can say that, and in SSE it can perform on integer plus floating point data, or decimal type data. Right, so definitely in order to perform SSE, okay, the microprocessor must need some registers, and that's XMM and some other registers. Alright, then after that I have actually added a slide on packed data, so I have already covered what is a packed data, so you can go through this slide. Okay, then we have a YMM registers, and YMM adds some the difference between XMM registers and the YMM register is the size. Okay, I guess XMM registers were only consist of max up to 128 bits packed data, and the YMM actually can support up to 256-bit packed data. So these are the I'm touching these things very briefly and from, like, let's say 1000 miles above. But definitely there are a lot of other minutiae that I'm not going to cover here. I just want to give an overview, a basic difference, basic explanation. Okay, one more thing that Intel IA32 processor has is MPX technology, protection extension, and that is, to me, it looks awesome. But when I was preparing this lecture, I came to know that this is just a sort of overrated type of thing. Okay, let me tell you first of all what is memory protection. uh, you know you guys have worked a lot with pointers, and the problem with pointer is bounds, bound checking, bounds. Like, okay, I give an example of integer. Okay, sorry, not integer, I mean arrays. In C or C++, there is no bound checking on arrays. Similarly, if you are using pointers, so you have direct access to that particular memory location, so you can go beyond your allocated or requested or reserved memory space. So when we talk about pointers and arrays, so the first thing that actually comes to the mind is the buffer overflow attack and buffer overruns attack, right? So in order to basically mitigate buffer overflow and buffer overruns attack, Intel, if I'm not wrong, back in 2013 they came up with so Intel Studio as well, their software that support the bound checking mechanism. But unfortunately, it was initially started to support by different compilers like GCC and the Linux kernel as well. But nowadays, which I know, that is GCC version 9.x doesn't support memory protection extension, and even now Linux latest kernel is also not supporting memory protection extension. What it does actually, it maintains another set of registers, right? And these are the 4 registers, okay, BND0 to BND3, that actually stores the upper bound and lower bound of the pointer. Like, for instance, you have declared a pointer, and now you have pointed that pointer to the memory location. Like, let's say that an array consists of, let's say that, I think I should use, yeah, this space. So let's say that array consists of only, let's say that, 4 elements, and the base address of the array was 0x101. This is 0x102, 0x103, and then 0x104. 101, I mean, this is just hypothetical addresses: 101, 102, 103, 104. So you can say that, okay, assuming this is a character array. Assuming if this is the base address, so this is the lower bound of the array, the starting address 101. Then this is the second, this is the third, and this is the fourth. So the max address, we can say that 0x105. So what happens in these 4 registers, BND0 to BND3, the microprocessor in fact stores the lower and upper bound of the pointer that is pointing to that particular memory location, that array. And if any process or during the execution of that particular program, if any thread or any program statement or any instruction that tries to access the memory region beyond, I mean below 101 and above 105. In fact, it is ends at 104. Okay, above 105 will not be granted. So this was the MPX extension, MPX technology introduced by Intel. Initially, it was supported by different compilers, even Visual Studio. I guess I do not remember the version, but Visual Studio developed experimentally started to support MPX technology. But as I just said, GCC doesn't support now. Linux kernel has removed the code for MPX. And the bad thing about the MPX was, even there are a lot of protection features provided by MPX. Still there are hardware vulnerabilities. It's still there. It doesn't, we can say that it provides 100% safeguard. No, there are many events, there are many vulnerabilities being identified where MPX technology has been compromised. Stack is very common thing, and all these things. Stack everything. When you call an instruction, when you call a function, it goes, what happens to stack, what things are pushed to stack, and what things are popped back to stack from stack. All right, so any questions so far? Let me check the time. Okay, I think I should. Okay, so let's see the additional resources. IO ports. IA32 architecture supports a transfer of data to and from the IO devices like IO ports, control registers. It supports many memory management registers, GDTR, LDTR, IDTR. Okay, debug register, we discussed earlier, debug and trap register. Memory type range register are used to assign memory type to regions of memory. Okay, and there are different additional features which are provided by IA32 processor these days. So you can go through these small definitions, and if you have any query, you can come back to me. Yeah, here this is a pictorial representation. Okay, and let's discuss about it. This pictorial representation actually shows you everything in general that we have covered today. Here is the address space, and if it is 32-bit processor, so the address space starting from 0 will go max by 2 to the power 32 minus 1. Here are 8 32-bit registers. These are general purpose registers. Then we have 6 segment register, CX, BX, DX, EX, and FX and GS. Then we have E flag register. Then we have EIP. We covered all these registers in the first lecture. Then we have FPU register, floating point registers. Okay, so in IA32 processor, we have eight data registers, and the length of every data register is 80 bits. Then we have a control register, status register, tag register, opcode register, and bunch of some other registers. Okay, and here you can see the FPU instruction pointer, IP, 48 bits, and then we have FPU data pointer register, again it's 48-bit register. Then we have MMX registers. We have 8 64-bit registers. Then we have XMM register. We have 8 128-bit register. Okay, then we have YMM register. We have 8 256-bit registers, and we have a bound registers, 4 128-bit register, and we have a bound. Okay, I skip few things. One, this register is used for user mode, and there's a concept called user mode and the kernel mode. Hopefully you will learn in future. And this is the bound status. If anything happens wrong, this status flag turn up. Okay, So the basic execution environment for a 64-bit processor, let's talk about this thing also. In 64-bit processor we have a maximum and if we follow linear address space, we'll see, as I said, we'll see in future linear address space, then we can have 2 to the power 64 bytes, okay, of maximum addressable space. But with the help of physical address extension, if you use physical address space, then we have 2 to the power 52 bytes, okay. Okay, software can query CPU ID for the physical. Okay, like for instance, if you are developing a software and you don't know whether your system is using linear address space or physical address extensions technique, so you can use CPU ID registers. CPU ID registers are special registers, okay, and these registers contain some information related to CPU, like the current operating mode, like whether it is running in the protected mode or some other mode, or the size of the of size supported by the processor, okay, in terms of, you know, number of bits, etc. So you can query the CPU ID registers to get information, and then accordingly you can basically have the required logic built into your application, okay. If you remember, the we in 64-bit processor we have 8 extra general purpose registers, okay, right. And I think there is nothing new in this slide, we have already covered it. And XMM register, YMM register, bound check register, stack. The stack pointer size that you need to, that's important. The stack pointer size is 64-bit, okay. The control registers, the debug registers, so it contains a lot of, you know, things. The one more thing, that descriptor table register, okay. Let's talk about descriptor table register. So descriptor table register here in 64-bit, we have, it is expanded to 10 bytes, okay, and interrupt descriptor table IDT also expands to 10 byte. Alright, and similarly the local descriptor table and task register table also expand to hold a full 64-bit address space. And this is the block diagram for 64-bit. You won't see much noticeable difference except the size of few component, like the addressable memory, okay, like the number of registers, and their sizes, and that's all. I don't think so you will see in this particular diagram that you will see a lot of difference in a 32-bit block diagram of a microprocessor and a 64-bit microprocessor block diagram. Alright, so any question? Thank you.